Let's do a side-by-side comparison of VHDL and Verilog, the two dominant hardware description languages. VHDL tends to be used more by defense and government agencies. Verilog tends to be used more by commercial. VHDL tends to be used maybe a little more in Europe. Verilog tends to be used more in the US. So I wrote a Blinky program in VHDL and in Verilog. Let's do a side-by-side comparison. All right, so here they are. So VHDL is on the left, Verilog's on the right. VHDL starts its comments with a dash dash. Verilog starts them with a slash slash. In VHDL, you have to define your libraries up front. So this is a standard IEEE library that's almost always used. Almost always use standard logic. If you do any math, you need numeric. Real helps you with some log functions and a few other things. And work is your local library. I think it's probably frowned upon now to actually define that, but I've got it here anyway. Let's see. Both have like a unit, a block, and so in Blinky it actually in a VHDL. They've got two concepts, but which we'll talk about in a moment. But let's say that in VHDL they call their units an entity, and in Verilog they call it a module. And in VHDL you need this is word keyword after defining your entity. Both have a concept of passing in constant type arguments. In VHDL, they call them a generic. In Verilog, they call them a parameter. You can see the slight syntax difference. You can also see that this guy's got this. So in Verilog, you start with a pound sign, and you do not have any punctuation after this closing parentheses. In VHDL, you don't have the pound sign, which is easy to remember, but you have this semicolon, which I usually forget. Then after the generics, they both define the signal input outputs, which VHDL identifies and calls out specifically as a port. There's no structure here on it's just parentheses and the port signals. The ordering is slightly different from the port list in that in VHDL, you start off with the signal name, the direction, and the type. And in Verilog, it's the direction and the signal name. Not much difference though. The entity then gets ended in VHDL, and then they start an architecture. And this allows you to have multiple architectures, so you could have a synthesizable version that's optimized for like speed or area. You could have another version that's like a behavioral model, which helps you and you maybe simulates faster. In reality, I rarely see anybody having more than one architecture for an entity, but it's still a reasonably cool concept. So in this case, the architecture, you give it a name. Since this is synthesizable, I called it RTL, which stands for Registered Transfer Language. Sometimes people put in synth. You can call it anything you want to for the architecture type. And then this Blinky lines up with the entity name. So you put the entity name here. And then is, again, nice keyword here. And in Verilog, you just have the module, no entity architecture concept. Then we get down to the signal definitions. In VHDL, we have a signal name, and type, and type. And in Verilog, they have this keyword reg, short for register, and then the size, and then the name. They also have the notion of a wire in VHDL. Signal registers and wires are both called signals in VHDL. Then we fall down into the the code that actually does something. It's called a process in VHDL. It's called an always block in Verilog. Both have like a parameter that's passed into it, which is called the sensitivity list. So in VHDL, whenever clock transitions, it calls this process. In Verilog, whenever there's a positive edge on the clock signal, it calls this block. So a slight nuance difference. And then, like in VHDL, you want to qualify, was it the rising edge or the falling edge that actually got you into here? If it's a falling edge, usually you don't want to do anything. If it's a rising edge, then you usually want to do something. So in this case, if there's a rising edge on clock, then do all the work. You don't need that over in Verilog because they've already got it defined with this pos edge word. You can also use neg edge, or I believe you can leave that off completely, and then any transition on clock would fall through just like in VHDL. So in this case, then we fall down into this if statement. With if statements, Verilog requires you to have parentheses around the conditional. VHDL does not. Verilog uses the double equal sign. VHDL uses a single equal sign. Verilog, you can just put in this like integer value. Oftentimes, though, you might put in a size like 1 tick B0. That helps some other tools, linting tools, pass those checks, but it's not required. Then in VHDL, you have the keyword then, and in Verilog, they put in the keyword begin. Going back up to this part here, another thing that always confuses me is that in VHDL, each one of the ports is separated by a semicolon. In Verilog, each one of the ports is separated by a comma. So I never remember which is which because I bounce back and forth between both. All right. So here, both of them use like pretty much the same type of assignment. Like registers use this. They both use this this whatever you want to call it, greater than sign, equal sign. It represents what's referred to as a non-blocking assignment. Almost always inside of processes, you want to use a non-blocking assignment. So these are pretty much identical. Verilog allows you to use blocking assignments, which is just plain equal sign. That is probably used more for, well, let's not get into that. Let's just show right now that the assignments are pretty much identical. Um, in in uh, in Verilog, it's just like, so we're just assigning 0. You could potentially do something again like 1 tick B0 and the 1 represents the number of bits, and the tick B, like this tick H, represents binary, or this H represents hex. In for in VHDL, you got this LED, which is a standard logic signal up here. Standard logic is essentially a 1-bit value, and it's kind of, you could compare it to regular normal languages. You could view it as a character, and like in C, a character is surrounded by a single quotes. So you got single quotes. Now here you're assigning this count to a 32-bit value of 0. In Verilog, in VHDL, they got this notion of this others assignment. It's a little bit tricky. View it as this just means 0. So that means so what it looks like, this is like a slicing type of thing that allows you to say certain bits are 1, all other bits are 0. And since we're not mentioning the other certain bits, we're saying we're not mentioning the certain bits that are there. It means everything is the other, so everything gets assigned to 0. A little goofy, but you get used to it. Now here's the notion of an else. So in VHDL, you have a then and then an else, and then an end if. In Verilog, you have an if condition begin, end to close that off, else begin. You can put this on multiple lines if you wanted to. Stylistically, this is kind of equivalent to like the cuddle style in C, if these were like closed parentheses and open parentheses. But it, I think, definitely comes out a little cleaner in VHDL. Then this is an assignment statement where we're assigning 1 bit of this counter to the LED standard logic vector. So this counter is like the 1 bit, it's a parentheses around it. In Verilog, it's a square brace that's around the bit that's being selected. Then this count incrementer, same in both languages. In VHDL, like whenever you end, like this end, you have to tell it, what are you ending? So I'm ending an if statement, even if it's really an else. If over in Verilog, you just say end for the always block. Here you say end of the process, so you know it's an end. It's a little more verbose. It tends to give slightly better error messages because it's got this extra. Either way, it's pretty much fine. In Verilog, you end the module with the keyword end module, and in VHDL, you end the architecture with the line end architecture RTL. And also, let's you do some variations. So you could do end RTL, which is the name of the architecture, or you can say just end architecture. I did both of end architecture RTL. And so that is the difference between 2 RTL blocks that would go inside an FPGA. Now let's take a quick look at 2 test benches. Here we go. And scroll up. All right, again, the comments are slightly different. In Verilog, they got this notion of a time scale. So you set it to something 1 nanosecond / 1 picosecond or 100 picoseconds or 1 nanosecond, 1 nanosecond, whatever. They don't have that notion at all in VHDL. I don't think it loses anything because of it. Again, in VHDL, we define all of our libraries. Again, an IEEE library is very common. Then again, we start with an entity. On VHDL, we start with a module, but it's pretty much very similar. Module TB. So TB is the module, is the test bench, is the module name. TB is the entity name. Then we roll into it, and since it's the top level, there's no ports. And then we just roll into the architecture here. And so one of the slight differences is, so we have all these signals defined up in the top of the architecture before the begin statement in VHDL. In Verilog, we can, like, this guy here is defined in both. But you can potentially define things sprinkled throughout. So you can put your declarations of signals, integers near your code. Some people like that, some people don't. I think for the most part, people tend to keep everything at the top. Um, then we have to generate a clock. So here's two different ways of generating a clock. There are other ways in both languages, but here it's just very similar. We've got a process versus always. Got a begin. Got a here very clearly stated wait for 5 nanoseconds. Here we have a pound 5, which means wait for 5 time units, of which the time unit uh, is right here, 1 nanoseconds. Then we have to instantiate our device under test. And so that's in this area here on in VHDL. We've got the instance name followed by entity and the entity name versus in VHDL Verilog we have the entity name followed by the parameters followed by the instance name. So the instance and the entity are swapped between the two different languages. And that is why I get that messed up all the time. Um, uh, Here we've got the generics following this following, and here they kind of just jam the generic in there between the two. Whatever. Then we got the port map, of which we got the internal name, this kind of directional, and the external name. Here um, we've got the internal period, internal name, parentheses, external name. Both lists are separated by commas. Um, and then we fall down into the main initial block. Um, in in Verilog, we have the notion of an initial block, which means that it'll just run one time and then stop, versus those always blocks, which when it's done, it kicks back up to the top. Um, VHDL doesn't have that concept. It just has a processor. There's not a initial process and an always process. It's just a process. And then both of them have a begin. Um, as far as printing out, in VHDL, we use a report. Um, and then you do an AND for string concatenation and a toString to do a conversion to string. So basically this creates a string and then gets reported or printed out. In Verilog, you have a dollar display, which prints it out. Here I'm putting in a dollar time. The reports always put a time and precede the message with a timestamp. Um, Here is how you wait for one clock cycle. And so in VHDL, it's a little wordy but clear. Wait until rising edge of the clock. Not bad. In Verilog, it's terse, but it's does its job. So at the positive edge of system clock, proceed. So um, both of them is very similar in implementation. Then again, it's an assignment. Again, it's considered like you can view it as a character. So it's sort of the values are for standard logic is surrounded by single quotes. There's a slight difference. So in Verilog, they have the notion of a repeat. So you repeat this in the between the begin and end 10 times. Uh, VHDL does not have that concept. So you'd have to say for I in 1 to 10 loop, blah, wait the clock, end loop. And so both of those are how you would wait 10 clocks. This is more, I guess you could say, Pythonic from on the VHDL side. Um, and then again, here we're assigning a reset. Let's see. So if you are doing a for loop, both languages support a for loop. VHDLs is again Python style with instead of a range, you actually specify the keyword range. You just specify the range. So this loops from 0 to 9999. The keyword loop at the end. And VHDL, you have 4 with some parentheses and a very C-striped type of structure, except that you can't do an I++. You need an I equals I plus 1. And then the loop is between the begin and the end, whereas in VHDL, it's between the the loop, and end loop. And we're waiting for clocks. It's the same as both. Here we're doing a comparison to see if something is not equal. In Verilog, that is with the exclamation mark equals, and in VHDL, it's with a slash equals. Some comparisons. So this is waiting for a small amount of time. So again, this would wait for 1 time unit, which in our case is 1 nanosecond. Here we're saying wait for 1 nanosecond. And sometimes you need to do that when you have signals because you want to make well, you just do. Here we're doing an equality. In Verilog, it's a double equal sign. In VHDL, it's a single equal sign. Here's a report versus a display. Again, Verilog is C style, like a printf. And this is like an old style. VHDL is like an old style Python. Here, it's a not equal to. So like again, we don't need the parentheses with VHDL. And we use the keyword not versus in Verilog, where we have an exclamation mark is the not, and you need the parentheses. Similar. Here, like this first time, it's a Boolean, so we actually have true and false in VHDL. And in Verilog, we pretty much still mostly like a 0 and 1 type of world. And I think displays, comparisons. Here's how you stop the simulation stops when you hit the finish in VHDL or the $finish in Verilog. And then as far as creating waves, you actually embed this into your Verilog testbench code here in, uh, in VHDL. You would essentially turn on the waves up in the command that you're running to run the simulation. And I think that pretty much covers the 2 main blocks that I've got. Languages really are not that different. I know there's a big religious war between the two, but for the most part, they both work. They're both fine. I think that's it.